Hi, my name is Yan, and today we're going to talk about electrode boilers. We'll figure out what exactly an electrode boiler is and how it works, without any complicated jargon and in simple terms, so everything is easy to understand. Right here in front of me, as you can see, I have three items. There's the GAZDA BE series, which is a three-phase boiler, and the single-phase GAZDA KE series boiler. Plus, we've got some electrodes from a Galan electrode boiler. Using these examples, I'll explain the principle behind how electrode boilers work, along with all the important details and nuances. Basically, we'll start with the simple stuff and gradually move toward the more complex parts. For this, I'll first saw open two GAZDA boilers. Look here, this is a GAZDA BE series boiler. Inside it are three electrodes. Because it's three-phase, it can be either a 3 kilowatt or a 6 kilowatt boiler in this casing. In this particular case, these electrodes are from a 3 kilowatt boiler, so this one is a 3 kilowatt model. And this is a KE series boiler, single-phase. It works on the same principle, but is designed for 230 volts. That's why there's only one electrode inside. Here it is, right here. Judging by the length of this electrode, this boiler is a 2 kilowatt model. So I've taken the smallest, or you could say, the weakest boilers as examples. And these are electrodes from a Galan boiler. Different models use different materials, but the principle remains exactly the same. The electrodes transfer electricity into the water, and that's what creates the heat. So here we don't have the traditional heating elements that heat up and transfer heat to the water. Instead, the heat transfer fluid itself is directly involved in the heating process. This makes the boiler quicker, more efficient, and eliminates issues with scale buildup. But we'll talk about scale, deposits, and all those details a bit later. Now, let's figure out exactly how the water is heated in an electrode boiler. Like I mentioned, there are no traditional heating elements here, no coils or spirals. Instead, the heating fluid itself becomes the heating element. The electrodes receive electrical current. In this particular case, it looks like this. Three phases go to the electrodes, while the neutral and ground connect to the boiler's housing. Or, in the case of Galan boilers, three phases, neutral, and ground also to the housing, although here there's no housing at the moment. And in the GAZDA KE series, which is single phase, we connect the phase here and the neutral to the housing. There's no ground here because it's not needed. Since the boiler is covered with this plastic coating, only the neutral is connected. Now let's talk about the power output of electrode boilers. Unlike traditional heating element boilers, which have a fixed power rating, electrode boilers vary their power depending on conditions. Let's see exactly what factors affect this. Factor number 1 is voltage in the electrical grid. This has the smallest impact. Typically, in single-phase systems, we've got 230 volts, and in three-phase systems, 400 volts. If the voltage dips a bit, for example, down to 220 volts instead of the usual 230, the boiler's power output will slightly decrease. But it's not critical, since voltage at home is generally pretty stable. We don't really have much control over this factor. It all depends on the electrical network. Factor number 2 is the distance between the electrodes. This is another thing that you, as a user, can't really influence. The distance I'm talking about is either between the electrodes themselves, like here, or between an electrode and the boiler's casing. Basically, the greater the distance, the higher the water's resistance, and therefore, the lower the boiler's power. In factory-made boilers, this distance is already precisely calculated, so practically speaking, we can't change it either. Factor number 3 is the surface area of the electrodes in contact with water. This parameter has a stronger influence, and in theory, it's something we can control. The larger the electrode surface area touching the water, the higher the current, and therefore, the more powerful the boiler is. This means the electrodes can either be thin and long, like in Galan boilers, or thicker and shorter. The main thing is the total surface area. Simply put, the longer the electrode, the greater its surface area, and the more powerful the boiler. Conversely, the shorter and thinner it is, the less powerful it'll be. And finally, the most important factor is the electrical conductivity of the water. In an electrode boiler, water acts as the conductor. The more salts and minerals it contains, the better it conducts electricity. If the water is too pure, close to distilled, the boiler simply won't work. I'm saying water just to keep things simple. But strictly speaking, it's better to call it a heat transfer fluid. We'll get into that a bit later. What's important to remember is that this heat transfer fluid needs to have a specific electrical resistance. Now let's figure out how exactly the power output of an electrode boiler is formed and how you can influence it. Power is essentially a combination of factors. The first factor is voltage. In physics, power is voltage multiplied by current. So, if we change the voltage, the current changes, and thus, the boiler's power changes. But at home, you can't practically turn 400 volts into 500 volts, or make 230 volts into 300 volts. However, in our product line, we have a special single-phase boiler called the GAZDA GM106. Its core function is adjusting the power by varying the voltage supplied to the electrode. With this knob here, you can directly adjust the boiler's power, setting it exactly as needed. We also offer separate controllers designed specifically for electrode boilers, the KROS 110 and KROS 325. There are detailed videos about these controllers on our channel, so you can check them out for more information. And these controllers work specifically as standalone regulators. They adjust the supplied voltage and current to the boiler, allowing the boiler to become either less powerful or more powerful as needed. And this GAZDA GM106 is already a single-phase boiler model with its own built-in regulator, essentially a built-in KROS. In all other cases, you can't really change your home's voltage. You supply voltage to the boiler, and based on the heat transfer fluid's resistance, the boiler produces a certain power. But we'll talk about that shortly. One important point I want to mention is that you can actually connect any electrode boiler to a single-phase network. Absolutely any of them. You just connect one phase here. Distribute the wires separately to the electrodes, well, not exactly parallel, just individually connected through 3 separate circuit breakers. That's it. The boiler maintains its original power rating. For instance, this boiler is 3 kilowatts, so each electrode will deliver about 1 kilowatt. It might seem like you're reducing the voltage, but you're actually increasing the electrode surface area interacting with the water. Essentially, it balances out. The boiler doesn't lose its total power, and you gain the ability to control its output in steps. The only thing you need to consider is the technical capabilities of your home electrical system to handle a specific boiler's load. But theoretically speaking, you can connect any electrode boiler to a single-phase network, even a 25 kilowatt or a 50 kilowatt model, though that's mostly theoretical. Usually, electrode boiler manuals specify connecting 6 kilowatt or 9 kilowatt boilers to either single-phase or 3-phase networks. For higher power models, manuals don't typically mention single-phase connections. However, as I said, you can technically connect even a 12 kilowatt, 15 kilowatt, or any other higher capacity boiler to a single-phase network, provided your home's electrical system can handle it. The next important factor is the electrode's surface area in contact with water. I've got a separate electrode here to show you clearly what I mean. Imagine we slide a heat shrink tube over it and heat it up. The heat shrink takes the electrode's shape, and the electrode stops contacting the water in this covered area. Only this remaining exposed part of the electrode stays active. As a result, if we roughly cut the active area in half, power of the boiler also drops by half. Or to make it even simpler, if you just physically cut off part of the electrode, you achieve exactly the same effect, a reduction in the boiler's power. We've already covered how an electrode boiler works. Now the question is, how do you check your water? How can you know if your water is suitable or needs adjusting? Since the summer of 2022, we've been equipping the electronics for our boilers with meters like these. Here's a single-phase one, and here's a three-phase meter. But they're not just electricity meters. They also have another important feature. They show you the boiler's power in kilowatts and the current in amps. With these readings, you can easily understand what kind of water you're dealing with. Fill the boiler with water, switch it on, and take a look. We have a table here with two rows. The top row shows the current drawn by cold water at around 15 Celsius, and the bottom row shows the current at about 70 Celsius. Here's an important point. The current, and thus the boiler's power, at 15 Celsius is roughly 2.5 times lower than at 70 Celsius. You have to keep this in mind. This is how any heat carrier behaves when heated. So once you fill your boiler with cold water, you check these readings. This way, you'll quickly know if your water is fine, meaning it has the right resistance, or if it needs to be adjusted. Here's another important point about voltage when using an electrode boiler. Does voltage affect the boiler's operation? Well, actually no. It doesn't really affect the boiler itself at all. Whatever voltage you supply to the electrodes, that's the voltage it works with, and the boiler will just give out the corresponding power. So if you connect 3 phases directly to a 3-phase boiler, or 1 phase to a single-phase one, it'll work accordingly. But yeah, of course, nobody connects a boiler just like that in a raw setup. In real-world installations, there's always some kind of control system in between, and in most cases, it's a contactor. Now, with contactors, voltage does make a difference. That's because inside the contactor, there's a coil that physically closes the power contacts. And that coil is usually rated for 230 volts. So, let's say your voltage drops to around 170 volts. Well, that coil might not be strong enough to fully pull in the contacts. It might start buzzing, vibrating, and if it keeps doing that, eventually the contacts will start to burn or even weld themselves. Worst case, the contactor just fails completely. Sometimes you also get these tiny, fast click, click, click sounds, kind of like a fast rattle. That can happen if there's a bad connection on the coil terminals, A1 and A2, or just unstable voltage in general. In that case, the coil keeps trying to close the contacts, but can't really hold them. Now I'll show you all of this. Also, yeah, sometimes the contactor itself is just cheap or poor quality and doesn't last long. So you end up with problems even if your voltage is okay. So, to sum it all up nice and clear, voltage is really important for the contactor, but for the electrode boiler itself, not at all. But if we're talking about GAZDA boilers, let's go back to the GAZDA GM model. Then the whole idea behind how this electrode boiler works is, as I've already said, adjusting the voltage and therefore the current that's being sent to the electrode. So, it really doesn't care what voltage you feed into its control side. Of course, it has its limits, but low or high voltage in the grid isn't a problem for it at all. Same goes for the KROS controllers, KROS 110 and KROS 325. They work on the exact same principle as this boiler. So let's talk about something pretty important that a lot of people worry about. What if, say, all the water leaks out of your electrode boiler, but the power is still on? Like, is that dangerous? Will something burn out or short circuit? And here's the cool part. Nothing's gonna happen. Seriously, nothing at all. The electrodes, well, they'll just be sitting there, not touching anything. Basically, they're just in the air. And since there's no water to conduct electricity, the circuit's open. No power flows through, so nothing gets damaged. That's actually one of the big advantages electrode boilers have over regular ones with heating elements or coils. So, why am I even bringing this up? Because this ties directly into another question I get asked a lot, and I mean a lot. Hey, can I install the boiler horizontally? Or, does it have to be mounted vertically? And here's the thing. Technically, yes, you can install it horizontally. It's not a strict rule. Water still flows through the electrodes and heats up like it's supposed to. But, and there's always a but, right? When the boiler's in a horizontal position, there's a chance air could get trapped inside. Let me explain what I mean. Imagine the boiler lying flat. Well, in that position, an air pocket can form up top. And if that happens, some of the electrodes might not even be touching the water. Maybe just the bottom one is submerged, and the others are sitting in air. And here's your return line, and here's the supply line. Or maybe one is half submerged. You get the idea. And here's why that matters. If an electrode isn't in contact with the water, it's not part of the circuit, so it won't do anything. It's like it's not even there. So how do you know if this is happening? Simple trick. Grab an ammeter and check the current going through each electrode. You should see similar readings on all three. If one of them shows a lower current, or maybe even zero, that's a red flag. Most likely that electrode is sitting in air instead of water. If it's mounted vertically, water fills it evenly, and there's no air trapped at the top. All the electrodes are fully submerged, and you don't have to worry about any of this. All right, now let's talk about wiring electrode boilers. And yeah, this part's going to be a bit more sensitive, more technical, let's say. We're talking about electrode boilers and RCDs, residual current devices. And the thing is, in most cases, electrode boilers just don't work properly when they're in the same circuit with an RCD. Why is that? Let me explain. Take, for example, the GAZDA BE series. In this boiler, both the neutral and the ground are connected directly to the metal housing. And that setup right away makes the RCD freak out. Basically, as soon as you connect the boiler, bam, the RCD trips. It just doesn't like that configuration. But since summer 2024, we've got something new, our three-phase GAZDA R series. These boilers are built kind of like the single-phase GAZDA KE series, where the whole body is covered in plastic. Same idea here. Even the threaded fittings, supply and return, don't actually touch the metal housing. So what happens? You connect the neutral to the body, and the three phases go straight to the electrodes. Just like in the single-phase version. One phase to the electrode, neutral to the body, and that's it. No ground wire needed at all. By the way, the same goes for the GAZDA GM series. At its core, it's basically a KE boiler. It's single phase, connects the same way, phase to the electrode, neutral to the body. But the GM model has one big bonus. It comes with a built-in knob that lets you adjust the power. That's super handy if you want more control over the heating level or to reduce energy use a bit. So from the perspective of RCD compatibility, it's a solid choice too. Whether it's KE, GM, or the three-phase R series, all of them are designed to work smoothly with RCDs right out of the box. Same goes for Galan boilers. Even though the neutral isn't directly connected to the metal casing, the base is made of plastic, and at first glance, everything looks okay. There's still a catch. The thing is, current can still leak through the water. And once you hook up a metal pipe, like steel or copper, it can easily make contact with the walls or other grounded parts of your home. So what happens? The RCD sees that leakage, from neutral through the water and the pipe, down to ground, and boom, it trips. Every time. Now, just one more thing that's worth mentioning. Even with KE, GM, or R series boilers, sometimes in rare cases, the RCD still trips. Doesn't mean the boiler is faulty. I had one such case with a client who was also an installer. He bought a KE boiler from me, installed it for his customer, and everything seemed fine. But the RCD in the house's main panel kept tripping. So I asked him, how exactly is the RCD connected? Turns out, the problem wasn't in the boiler, it was in the neutral line. My advice was simple. Make absolutely sure that the neutral going into the boiler is the exact same neutral that comes into the RCD. Not some random wire, not ground, and not a neutral from another part of the building. It has to be the same neutral wire that goes through the RCD together with the phase. He checked, rewired it as I suggested, and boom, it worked perfectly. No more issues. The boiler ran just fine. And the RCD stayed calm. So the key takeaway here is this. RCDs work based on balance. If the phase and neutral currents don't match, the RCD thinks there's leakage. So if you want your GAZDA KE, GM, or R series boiler to work flawlessly with an RCD, just make sure the neutral line is clean, proper, and coming from the same RCD unit as the phase. That's all it takes. All right, let's break it down. Where does the concept of power in an electrode boiler actually come from? At the beginning of the video, I said this one here is a 3 kilowatt boiler, and that one is 2 kilowatts. But wait, how do we know that? I mean, I could just write 9 kilowatts on the label, and what then? In fact, there are 4 main factors that determine how much power an electrode boiler actually gives you. The surface area where the electrodes touch the water. The longer the electrode, the more area it has in contact. The voltage supplied to the electrodes. The higher the voltage and/or current, the stronger the power. The distance between the electrodes. The closer they are, the lower the resistance, and the higher the power. Spread them too far apart, resistance goes up, power drops. And finally, factor 4, the conductivity of the heat transfer fluid. Now that one is both the most important and the trickiest. So where did all that add salt or baking soda to the water advice come from? So where does this whole thing come from? You know, add salt to the water, add some baking soda, and so on? Well, it goes back to the fact that most electrode boilers were originally produced in Russia and Ukraine. And over there, the water is different. By different, I mean it actually conducts electricity better. More salts, more minerals, and unfortunately, more metals too. Now, when people in European countries started buying those boilers, they were using local water, and it turned out the conductivity was lower. So what happened? The boilers worked, but they were noticeably weaker. To fix that, folks had to add a bit of salt or soda to bring the boiler up to its full power. In the summer of 2024, we finally measured the conductivity of tap water in Poland and other parts of Europe. And the results? Pretty consistent. Almost all tap water showed around 200 microsiemens, give or take a little. That's why we adjusted all GAZDA boilers accordingly. Now, they're designed and tuned for that standard 200 microsiemens level. which matches regular tap water in Europe. But just a heads up, if you're using well water instead of tap, it's a different story. Well water usually has way more minerals, salts, and unfortunately, more metals too. So its conductivity might be 2, even 2.5 times higher. And that means the boiler will be noticeably more powerful than intended. And that's exactly why the antifreeze fluids you find in regular hardware stores are no good for electrode boilers. I don't know the full story of how they're made or what exactly they're based on, but their main purpose is for solid fuel boilers, gas boilers, maybe even for standard heating element boilers, but not for electrode boilers. In those systems, electrical conductivity doesn't matter at all during production. So, when you pour that kind of fluid into an electrode boiler, it's a disaster waiting to happen. The conductivity of those store-bought fluids isn't just a bit higher than well water. It's 10, maybe 15 times higher. We're not talking 200 microsiemens anymore. We're talking 2,000 or even 3,000 microsiemens. And what happens then? You pour it in, and boom, your 3-kilowatt boiler suddenly behaves like it's running at 30 kilowatts. The current spikes instantly, and your circuit breaker trips right away. That's why, unfortunately, these types of fluids are just not suitable for electrode boilers. Now, you might be thinking, okay, but what if I just leave that store-bought fluid and reduce the electrode surface area by 10 or 15 times? Well, in theory, yes, it's possible. You could shrink the working area to balance out the high conductivity. Like, you take the electrode, put heat shrink tubing over most of it, or even cut it down to just a tiny little piece, and then pour in that superconductive fluid. But in practice, it doesn't really work. The boiler starts buzzing, making weird noises, and the system becomes unstable. Yes, technically it'll run, but it won't be efficient, and it sure won't be reliable. So yeah, long story short, that kind of heat transfer fluid is just not meant for electrode boilers. It's a mismatch, and there's no real workaround that makes sense. All right, let's figure out what boiler power you actually need for your home. This is probably the most common question I get: how to choose the right boiler based on your square meters. The rough rule of thumb is simple: 1 kilowatt per 15 square meters of heated space. It's not a perfect formula, but honestly, it works in 90% of cases. So, let's say your house is 100 square meters. You'd need a boiler around 6 to 7 kilowatts. What if you go with something weaker? Well, in mild months, like October, a smaller boiler might still cope. For example, if you go with a 3-kilowatt boiler instead of a 6, in October, it might be enough. But come January, when it's -5 or colder outside, that same boiler will be running non-stop, still pulling only 3 kilowatts, and just won't keep up. It'll heat, sure, but it won't get the system to the proper temperature, like 60 degrees Celsius. Now, if you follow that 1 kilowatt per 15 square meters square formula, most of the time your boiler will only need to work at about 50% of its full power. So for example, a 9 kilowatt boiler, on average, will consume around 4.5 kilowatt hours. In harsh winter conditions, yeah, it'll run more, closer to full power, but it'll be able to meet the heating demand when it's really needed. Now, let's bust the biggest myth, that a more powerful boiler consumes more electricity. No, a powerful boiler does not consume more energy. It's your house that consumes the energy. Heating is all about covering heat loss. Nothing more, nothing less. Your house loses heat through the walls, windows, roof, and floor. The boiler's job is just to generate enough heat to balance those losses. That's how you keep your home at a comfortable temperature, say 22 degrees. So whether you reach that balance with a 6 kilowatt boiler or a 25 kilowatt one, the energy consumed will be roughly the same. Let's say you need 3 kilowatts per hour to stay warm in winter. A 6 kilowatt boiler will give you that in a steady, gentle way. A 25 kilowatt boiler? It'll hit that target instantly, shut off, and wait until the temperature drops a bit before firing up again. So yes, the power consumption over time will be the same. The only difference is, a more powerful boiler creates a much higher load in the moment when it kicks in. That means your electrical system, wiring, breakers, has to be ready for that spike. That's the only thing to watch out for. Why is this myth so common? It comes from the world of solid fuel and gas boilers. With those systems, when a big boiler fires up, the flame creates more heat than the water can absorb, and the excess heat just goes up the chimney. So yeah, a bigger gas or solid fuel boiler really does burn more coal or gas. But that logic doesn't apply to electric boilers. They don't have chimneys. All the heat stays in your house. There's no extra heat being wasted. It all goes into your radiators, your floors, your rooms. The only thing that changes with electric boilers is the load. When a 25 kilowatt unit turns on, the wires feel that load. Unlike gas pipes, which don't care how hot the gas burns, your electrical wiring does care. It gets warm. Your breakers trip. Contacts heat up. That's why in electrical systems, load matters a lot. It's one of the key concepts in all of electrical engineering. There's one more thing I want to mention, a small but important detail. Sometimes when our customers buy an electrode boiler and at the same time install brand new steel radiators, and I'm talking specifically about steel ones, not aluminum, not bimetal, not cast iron. Everything seems fine at first. But then after about a month, they notice the boiler suddenly starts losing power. Why does that happen? Because during manufacturing, these steel radiators are treated with some kind of oily coating inside, probably to protect them during storage in the warehouse. And once the system is up and running, the hot heat transfer fluid slowly starts to dissolve that coating. Eventually, that oily stuff settles on the electrodes. And once that happens, the electrodes stop conducting electricity as well, which leads to a drop in boiler performance. This usually happens about a month after the boiler has been in use. So what's the fix? Simple. Just remove the boiler and rinse it out with something that dissolves grease. You can take the whole boiler off and flush it, or unscrew the electrodes and clean them separately. The goal is to get rid of that greasy film. That's it. All right, so now we've gone through the ins and outs of electrode boilers. I tried to explain everything clearly and in simple terms. Hopefully it all made sense. But hey, if something's still unclear, just drop a comment down below. I might make another video on this topic, or maybe even a few shorter ones where I cover each question or point separately, one by one. See you in the next videos.
Вопросу по небольшому пункту, по